Okay, this is going to be a video about what are called Kohonen networks. It's a kind of a neural network, but it's actually the self-organizing maps that we've talked about and that are that the program Discovery uh, produces. It's a kind of clustering. Just like k-means is a kind of clustering, it's another approach to clustering records, finding records that are similar to each other versus other records that are not similar. And this is a screenshot from this software called Discovery. It's an older version of Discovery. And over here on the left is the Kohonen map. On the right is a little bit different, so we won't talk about that right now. That's kind of an aspect of discovery more than it is of some maps or self-organizing maps. Kohonen networks were introduced in 1982 by the Finnish researcher Teuvo Kohonen, although they were applied initially to image and sound analysis. So he was using them to maybe do some things with images and sounds. Nevertheless, they're an effective mechanism for clustering, and a type of self-organizing map which itself represents a special class of neural networks. So actually, it's a neural network, but neural networks, usually we think of them as we use them to predict something or estimate something. This is different. The goal of self-organizing maps is to convert a complex high-dimensional input signal into a low-dimensional discrete map. So what does that mean? Well, in our case, we're going to take high-dimensional data. We've been working with tweets. So each word in our so-called dictionary is a variable, and so we have a lot of variables. But we're going to be able to somehow visualize all of those variables in a single two-dimensional map. And not only are we going to visualize them, but we're going to kind of group the records into similar groups. So what does that mean? Basically, it means that you take data that can be high-dimensional, i.e. each record or observation has many fields. So you have an observation or a record, and it has many fields, many variables associated with it. So not just like X and Y, but maybe 100 variables. And like I just said, we did that with tweets. We considered them as vectors in a very high-dimensional space, or the dictionary, the large dictionary which is high-dimensional, and you get a result that is usually two-dimensional. This result is sometimes referred to as a map. It is often said that maps preserve the topology of the original data. So what does that mean? That just means these maps, not all maps, but these maps, these self-organizing maps, preserve the topology of the original data. What does that mean? It means that records that are close to each other in the high-dimensional space are also close to each other on the map. Basically, it means that for records that were close to each other in their full dimensionality, they will again appear literally close to each other in the map. And you might ask, what do you mean by close to each other in their full dimensionality? In one sense, it means that the records represent individuals that are similar with respect to the variables being measured. So if they're close to each other in their full dimensionality, means with respect to all the variables being measured, they're similar. Mathematically, it means that after you choose a norm, which means a distance, well, yeah, more or less means a distance, that based on that norm or distance measure, the distance between the two records is small. And this is a picture of a typical SOM architecture. And this is the map here. And this map consists of what we call 9 nodes here. There are 9 nodes here, 9 nodes. And these are we're only inputting, in this case, just 2 variables. Now normally we would do this with, we could do this with many variables, but in this picture we're just inputting 2 variables, age and income. And this is like the neural networks. We have these weights associated with each of these nodes and each of these variables. So each variable is connected to each of the nodes, and there's a weight associated with them, with each one. Topology of a simple self-organizing map for clustering records by age and income. So suppose we just have 2 variables, age and income, and we want to, and we have many. Suppose we have many records, in other words, like many people, and we're just measuring 2 variables. We're just measuring their age and their income, and we're going to try and produce this kind of map that we're going to see it shortly. Okay, and also you see that this is called the input layer, just like before, and this is called the output layer here. The input layer is shown at the bottom of the figure with 1 input node for each field, for each variable. So we have an income variable, so that's 1 node, and an age variable, so that's a second node. And we only have 2 here because we're just talking about 2 fields or 2 variables. Just as with neural networks, these input nodes do no processing themselves, just like when you study the neural networks, the input nodes don't do anything except for just take the variable values, but simply pass the field input values along downstream. Like neural networks, each connection between nodes has a weight associated with it, right? So this line here has a weight, this line here has a weight, which at initialization, initially, is assigned randomly to a value between 0 and 1. So we saw that similar before. Unlike most neural nets, SOMs have no hidden layer. So if you remember the picture of a neural network, I think I have it here actually. Let's see if I can scroll back. Yeah, this was the one that we learned about before. This was a neural network. And here we have the input layer and the output layer, and then we had that hidden layer. And we had the weights associated. So the input you'd multiply by the weight, do some processing here, and then send that out, and so on. So we have, anyway, 3 layers. But for a SOM, for a self-organizing map, which is a kind of a neural network, but you don't have an input layer. Okay? Okay, unlike most neural nets, SOMs have no hidden layer. Okay, here's a simple example of a Kohonen network. Suppose that we have a data set with 2 attributes, age and income. Okay, so we just have data set with, and we're only measuring 2 things. So we're obviously talking about people, and we're measuring their age and their income. So we might have like 1,000 people, but we have just age and income. So in terms of like a spreadsheet, we would have just 2 columns, age and income, but we might have like 1,000 rows. Okay, in fact here we have only 4 people, and we have their age and their income. So this person's age was only 0.8, so they were pretty young. No, that's not what that means really. And this person's income was only 0.8, so they didn't earn very much either. No, that's not what they mean either, because we need to normalize the values. So actually the age is always going to be between 0 and 1, so this person being 0.8 might be an old person, because they're at the top of, they're at the high end of the scale between 0 and 1. and their income, if we've normalized income between 0 and 1 as well, then 0.8 for their income, I guess, is a high income. So we might say that this person is an older person with high income. And the next person would be an older person with low income, and so on. Here's a younger person with very high income, and a younger person with low income. And we're just going to denote this as x11, x21. I don't know what this means. These are just ways to denote these individuals. Suppose that we have a data set with two attributes, age and income, which have already been normalized. And suppose that we would like to use a 2x2 Kohonen network to uncover hidden clusters in the data set. So here, in this picture, we had a 3x3 Kohonen network. That's the output layer has 3x3, but we're talking about, suppose we just have a 2x2 Kohonen network. Now, you can set up the number of nodes to be whatever you want. Depending on how you set it up, you might, that's kind of like tuning the neural network, so it might work better or it might work worse. Simple, okay, suppose it, okay, we said that already. So we would thus have the topology shown here. Okay, so now we have the weights indicated as well. So W24 and W14, remember the notation before that we studied. So like W14 means it comes from the first one and goes to the fourth node. And W12 means it comes from the first node and goes to node 2 here. And here, W24 means it comes from the second node and goes to the fourth node. Okay, so we're going to use that notation. At initialization, the weights are randomly assigned. So just like before, we're going to randomly assign the weights at the beginning. Then for a given record or instance, a particular field value is forwarded from a particular input node to every node in the output layer. So the first person has an age and an income, and we're going to, so for a given record means or an instance, we're going to give a person, in this case a particular person, a particular field value is forwarded, so their age is their age field is forwarded here to all these nodes, and their income is forwarded also to every node in the output layer. It's forwarded, but of course we use these weights. We multiply the age by W12 and then send that here. We multiply the age by W11 and send that here, and so on. For example, suppose that the normalized age and income values for the second record in the data set are 0.8 and 0.1 respectively. So we saw that before. The second record was here, and the age was 0.8 and income was 0.1. Okay. Whoops, what did I do? Okay, there. So we have, suppose that we had those inputs. The 0.8 value would enter the sum through the input node associated with age, right? You can see down here. And this node would pass this value of 0.8 to every node in the output layer, but it would pass it as you'd use these weights to multiply that 0.8 through the income. Similarly, the 0.1 from here would be distributed through the income input node to every node in the output layer. Okay, simple example again still. These values, 0.8 and 0.1, together with their weights assigned to each of the connections, would determine the values of a scoring function, such as a Euclidean distance for each output node. The output node with the best outcome from the scoring function would then be designated as the winning node, i.e. the node which was basically closest to the incoming i.e. the node which basically was closest to the incoming record would win that record. Okay, for example, node 4 may win the incoming record. So the first record we said, or the second record, whatever it was, this one, 0.8, 0.1, this was age and income or something like that. And yeah, age and income. So we'd send that in here, and it would, so because of the weights, something would get sent to node 1, something would get sent to node 2, something else would be sent to node 3, and something else would be sent to node 4, right? Because all these weights are different. So when we multiply through by the 0.8 through the weights and the 0.1 through the weights, each one of these nodes, and we add that together, each one of these nodes is going to get something different, right? Now the nodes originally had some value already. Okay, now at the beginning maybe the nodes are random. These node 1, 2, 3, and 4 originally had some value. Maybe initially they're random, but they change. But even suppose they're random, still they have initially some values. Now what we're going to do is, we just said we're going to send this through the network so that some number based on the age and income is going to be sent to node 1, node 2, node 3, and node 4. Now, the node that is closest to what we're sending is the so-called winning node. Okay, so maybe what gets sent to node 1 is close to what node 1 already had. And maybe what gets sent to node 3 is far away from what was in node 3 before. And maybe what's in node 2 is far away. And maybe what's in node 4 is close to what it gets. Okay? So maybe node 4 is the one that wins because it's closest to what it receives from the 0.8 and the 0.1. Okay? So that would mean node 4 is the winner. So that would mean basically that we would assign that record, which record? This record up here, the one that had 0.8 and 0.1, I think that was the second record, would get assigned to this node. Okay? Temporarily, anyway. And we're going to do that for every record to see where every record goes. Self-organizing maps exhibit three characteristic processes: competition, cooperation, and adaption. Okay, so these are just words that they use to describe some processes. Competition. Competition, as mentioned above, the output nodes compete with each other to produce the best value for a particular scoring function. So when we say it's closer or not closer, we have to sort of define what we mean by close. Okay, so that's one thing that's hasn't been explained clearly, but we have to define what we mean by close, and we call that the scoring function. To produce the best value for the particular scoring function. In this case, the output node that has the smallest distance between the field inputs and the connection weights would be declared the winner. Cooperation. The winning node therefore becomes the center of what's called a neighborhood of excited neurons. So we said that number 4 was the winner before. So then if there were more than just 4 nodes here, suppose there were 100 or 1,000, then the nodes around node 4 would be kind of excited. Okay, so the center of a neighborhood of excited neurons. This emulates the behavior of human neurons, which are sensitive to the output of other neurons in their immediate neighborhood. In self-organizing maps, all the nodes in this neighborhood share in the excitement or the reward earned by the winning nodes, that of adaption. Thus, even though the nodes in the output layer are not connected directly, they tend to so the nodes are not connected in the output layer. So none of these nodes in the output layer are connected, right? They're connected to age and income, but they're not connected to each other. Thus, even though the nodes in the output layer are not directly connected, they tend to share common features due to this neighborliness parameter. Okay, and then finally adaption. The nodes in the neighborhood of the winning node participate in adaption, that is, learning. The weights of these nodes are adjusted. The weights of these nodes are adjusted so as to further improve the score function. In other words, these nodes will thereby have an increased chance of winning the competition once again for a similar set of field values. So, I don't know if this is clear or not. A little bit without numbers in here, it's a little bit tricky to see it. But so here, this node wins, and so the inputs from here and the weights and the associated weights were closest to what was already here. And so what happens is, but still they may not have been exactly the same as what was here. So what was here now gets adjusted a little bit so that it kind of looks more like what it was just sent. So it looks more like the record that was just sent to it. So that's kind of the prize that that's the adaption. And the surrounding nodes, if there were other nodes surrounding this, not just 4, but as I said, suppose we had 1,000 nodes, then there might be a group of that are kind of surrounding it in the neighborhood, and you define how big you mean by a neighborhood. But anyway, those would also sort of adapt to this particular record, because this one won it, so the ones around it also adapt to it. Okay, so let's read that. The weights of these nodes that are surrounding it are adjusted so as to further improve the score function. So they're closer to that one record that was just sent through, so it means their score is better. In other words, these nodes will thereby have an increased chance of winning the competition if a similar record comes in, because they've adapted to it, or to the one that was the original one. Kohonen network's algorithm. For each input vector, do competition. For each output node j, calculate the value d, which is the distance of the scoring function. Okay, let's say, first of all, I made a slight mistake a little earlier. See if I can get back there. Get back. So I said that there are some values in the nodes, which is not quite true. We just have the weights here. So going back to this. So this is a kind of more mathematical explanation of what we were saying. So we're going to take an input vector, x. So in the example, x just had income and age, so it's just two-dimensional. We could have more dimensions than that, but it's just two-dimensional. Okay, so for each input we have, so like the first person is the first input. For each output node, so remember we had 4 output nodes in in the diagram. Calculate the well, just to show you, we had 4 output nodes here, right? These are the output nodes. Okay. So calculate the value dwj, comma xn. So so let's look at this a little more carefully. We're going to, this is summing over I. So we have so for example, I might be first 1. So we would have w1j and xn1. w2j and xn2. And so on. So what does xn1, xn2, and so on mean? Well, we just said that x is a vector, and so it has a number of components, like the first component and the second component, like age and income. So that's what xn1 means, xn2 means, and so on. Okay, so the n means the first person, or the second person and the third person, and the I means the first person's age, and then the first person's income. So I would be 1 would be the age, and 2 would be the income. Okay, so we're summing over I. So that means in this sum, we're talking about first using the age of the first person, and then using the income of the first person. And that's going to be the 2 terms of the sum is only going to go from, since we only have I goes only from 1 to 2, we're only going to have 2 terms. And here is w1j, w2j. So let's go back and see what that was about. w1j and w2j. So here, w1, 2, and w2, 2. So these two, for example, w12 and w22. So what are they? Those are w12 is what's going to node 2 from age, and w22 is what's going to node 2 from income. So it's just the weight for age and the weight for income going to node 2. I hope that's clear. You can stop it and read it, I think. So what are we doing again? So we're taking, let's do it for 1 first. So we're taking w1j. What does J stand for? J stands for which output node we're talking about. So let's just choose an output node, like output node 2. Okay, so what are we doing? We're taking w12 and w22. But first we're taking w12 minus xn. N is fixed. We're not going to change n. xn 1. What is that? w12 is the age weight that's going into node 2 minus the value, the age, minus the actual age. Yeah, is that right? N. Yeah, that's right. Okay, so we're taking the weight minus the age, and then another weight minus the income. We're squaring each of those and adding, and we're doing that over over age and income. So that's like a distance of how far our x variable is from the current weights, from the current set of weights. Okay, so before I said something a little bit wrong, because I said we were considering the distance from the some value in the node itself, but it's not a value in the node itself, it's just the weight. Okay? So anyway, so we figure out how far our input is from the weights that go to node 2, and that would be when j was 2, and then we do this. So what do we do this? We say for each output node. So we had 4 output nodes, so we do it for the first output node for j equals 1, for j equals 2, j equals 3, and j equals 4. We do this. And one of these is going to be smallest. The distance between our age and income is going to be closest to basically one of the nodes, or one of the weight sets for the nodes. So the one that's closest, the node that has the closest weights to our input, is going to be the winner. And that's what I said before. So that's what this says. For each output node j, so for each of the output node j, calculate the distance basically of the input from that output node. Let's just say it that way. And we're going to do that over all of them, and then one of them is going to win. So that's what we mean by competition. Cooperation. Identify all output nodes j within the neighborhood of j, within the neighborhood of the winner. Capital J stands for the winner. So within the neighborhood of j, now as we said before, if you only have 4, there's not really a neighborhood, but if you had 1,000, you could talk about a neighborhood. Defined by the neighborhood size r. So you define what you mean by the neighborhood, like all the ones that are within 1 unit or 2 units. So anyway, you can define what you mean by close to the winning one. For these nodes, for these ones in the neighborhood, do the following for all input record fields. So you take the current weight and you add something to it. So you can figure out what this is. What you're getting, something about the distance from the current input to what you to your current set of weights, and then you multiply by some proportionality constant, and then you add that to the current weight. So in other words, you're just adapting. You're just allowing the current weights to be adjusted a little bit. The new ones will be basically the old ones plus a little bit of adjustment, hopefully adjusted towards the present input. All right? And then next, adjust the learning rate and neighborhood size as needed. So you can adjust how many of these that you're going to do this adaptation to, and how much adaptation you're going to do. That would this proportionality constant would determine that, right? And then stop when the termination criteria are met. So I guess that refers to the how many times you keep adjusting things. Okay, in our example with just 4 nodes, it's pointless to talk about a neighborhood of nodes, right? Just have 4 nodes. And it's pointless to talk about a radius r to define such a radius. However, if you have a map of 500 or 1,000 or 1,500 or 2,000, this kind of discussion makes sense, and weights of the nodes in a neighborhood of the winning node are adjusted to be more similar to the record that has just entered the system. Okay, cluster validity, another concept. To avoid spurious results and assure that the resulting clusters are reflective of the general population, the clustering solution should be validated. One common validation method is to split the original sample randomly into 2 groups, develop cluster solutions for each group, and then compare their profiles. So hopefully the profile should be somewhat similar because you did it randomly. You randomly divided the group into 2 groups. So the clustering should be somewhat similar. Okay, let's try and look at an example of this. Application of clustering using Kohonen networks. Churn, also called attrition, is a term used to indicate a customer leaving the service of one company in favor of another company. So maybe you are currently a customer of Docomo, but you saw the new Google Android phone at um, SoftBank, and you like it more than what Docomo has, and so you might be an example of churn, or you might attrite, or you might leave Docomo in favor of SoftBank. Okay, so that's what we mean by churn. And companies are concerned about churn. Obviously, they don't want to lose their customers. The following data comes from the UCI repository. The UCI repository of machine learning databases at the University of California, Irvine. So if you go there, if you look this up on the internet, you'll see there's lots of data there. Now, we haven't had such a problem with having data these days because we have all the tweets. But if we didn't have those tweets, we'd need data to work with, and we could go to this site and get data. And their data is mostly numerical. It's not text like we're using in the tweets. 1. We will consider the following scenario. A telecom company is monitoring its customers to understand, to predict, and hopefully to take measures to decrease churn in its customer base. So they're concerned about churn. They want to understand who's going to churn. They want to predict it, and they want to take some measures to reduce the possibility or decrease churn in its customer base. And the data set contains 20 variables, so that's kind of a lot. Not nearly as much as we've been dealing with Twitter, but anyway, it's kind of a lot. Especially, well, anyway, it's kind of a lot. The data set contains 20 variables worth of information about 3,333 customers. So that's the number of records, along with an indication of whether or not that customer churned, whether they left the company. Okay, so we have 20 variables plus one more, and that is, did they leave the company or not? So we could build a regular neural network to predict the churn, but that's not what we're going to do here. I guess we're going to do something else, but we could do that. We could predict the churn using the data that we have. These 3,333 customers would be a data set that we could build a model on. Anyway, the variables, the 20 variables, are as follows. The state, the account length, the area code, the phone number, the international plan, voicemail, number of voicemail messages, total day minutes, total day calls. Okay, let's see, what are these? State. Well, that's just which state they come from. The account length. That's an integer, and it indicates how long they've been a customer, how long the account has been active. The area code is a categorical variable. That's kind of weird, but well, no, it's not weird, because the area code is not, we don't really think of it as a number anyway. Even though it is a number, we don't treat it like a number. We don't add them or anything like that. So, okay, it's categorical. The phone number, which is essentially a surrogate for customer ID, or we could use it as a customer ID. International plan is a yes/no variable indicating whether they have an international plan or not. Voicemail plan is also a yes/no variable indicating whether they have voicemail or not. So remember these words: dichotomous, categorical. Dichotomous means yes or no, or having two values, two levels, and categorical, you know what that means. Okay, number of voicemail messages. So that's how many voicemail messages they've received. That's an integer. Total day minutes, which is apparently a continuous variable, which is the minutes customer used used the service during the day. I don't know what that means exactly, but total day calls, that's just how many calls they made during the daytime, I guess. Then we have some more variables. Total day charge, so not how many minutes they made, but how much money they spent in day calls. Total evening minutes, that's how many minutes they used it in the evening. Total evening calls, I guess that's the number of calls, not the number of minutes. Total evening charge, so that's again probably like they say here, it's probably the product of this times this. It's the amount of money they spent. And total, oh no, sorry, that's not right. I don't know. Yeah, it's a function of these two, but it's not their product. Total evening charge. Total night minutes. Okay, evening, night, those are different apparently. Total night calls, total night charge, total international minutes, total international calls, total international charge, number of calls to customer service. Okay, so we have all of those variables apparently. So that's a kind of a lot of information that the company could use to understand the customers. Maybe using those variables they could, know, like if people make a lot of calls to customer service, maybe those people are candidates for churn. Maybe they might leave or whatever. Anyway, we might be able to build some kind of model to predict that. But all right, the following variables were passed to the Kohonen network algorithm using Clementine. Now Clementine is like Weka, but it costs about $20,000 to $50,000 as opposed to Weka, which is free. And the way I see it, it's not much better than Weka. In fact, it seems actually worse than Weka. But anyway, flag. Okay, so these are the variables that they're going to use in their like Weka or in Clementine. International plan and voicemail plan. So those are yes. Both of those are yes/no variables, 0, 1 variables, or flag variables. And then numerical variables, we're going to use account length, voicemail messages, day minutes, evening minutes, night minutes, international minutes, and customer service calls. So I guess we're not going to be using all the variables. I'm not sure, but or maybe it seems like they're planning just to use a subset of them. Okay, and we're going to put this into our Kohonen net. So these are the variables down here. These are the input variables. So voicemail plan, international plan, account length, voicemail messages, and all these other ones. Okay. The topology of the network is as shown. So the setup is like this. So we have all these input. This is the input layer, and we're going to do a 3x3 for our output layer, with every node in the input layer being connected. I don't know if we have a picture of that or not, with weights not shown to every node in the output. Okay, so this is the topology of a 3x3 network, and the labels here, you can understand them, right? This is 0, 0, this is 1, 0, this is 2, 0, 0, 1, 0, 0, 0, 1, 0, 2, and so on, right? You see the labels. So I guess what? This means what? It's in the, I guess, no, it doesn't work so well. Anyway, you can understand the labels it's very simple. Okay, so they did it. They put this in, the 3,333 customers, and all those variables. How many variables were there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 variables, but so, if we wanted to show 9 variables, you couldn't do that, right? We can show 3 variables in a normal graph. Usually we only show 2. We could show a 3-dimensional graph, a 3-dimensional coordinate system, but after that we can't do it anymore, right? But this is a way to show all of these 9 variables in just a 2-dimensional graph. So here's the result. Now it doesn't, we don't know what it means, but here it is. The Kohonen learning parameters were set in Clementine as follows. For the first 20 cycles passes through the data set, the neighborhood size was set at r equals 2. So what that means that, like, I guess r equals 2, probably it seems to mean that everything is in the neighborhood of any particular node, right? Because this is only from here, suppose this was the node, this is only 2 away, I guess. I'm not sure if that's considered 2 or not. I think it is. So everything is in the neighborhood of everything else if you define r equals 2. And the learning rate was set to decay linearly starting at 0.3. So you have the learning rate, first you have it at 0.3 for the first round of the data, and then you let it decay, I guess. Then starting for the next 150 cycles, so remember what we mean by cycles, we're going to run all 3,333 records through this network, and then we're going to do that again, and again, and again, and again, so 20 times. And then we're going to do 150 cycles. And in that case, R was set down to 1, and the learning rate was allowed to decay linearly again, I guess, from 0.3 to 0. As it turned out, the Clementine Kohonen algorithm used only 6 of the 9. So remember what we're doing is we're sort of like taking the records and assigning them. So each node will, might win a record. Okay? So finally what happened was there were 9 nodes, but only these 6 won any records. So these 3 in here didn't win any records. Okay? So as it turned out, the Clementine Kohonen algorithm used only 6 of the 9 available output nodes, as shown with output nodes 0, 1, 1, 1, and 2, 1 being pruned. Or these here, there were 3 here that weren't used. Note that each of the 6 clusters is actually, each of the 6 clusters is actually constant value in this plot, such as 0, 0, 1, 2, and so on. So so you really just have one single dot here, one single dot here, one single dot here, one single dot here. So that's not very easy to visualize. So what they do is they say a random shock, which is just like an XY agitation or artificial noise, was introduced to illustrate the size of the cluster membership. So by doing that, you can see that like this one probably has fewer dots than this one. If they were all just right on a single point, you would have no idea how many were included in each of the clusters. So they did that. Okay? All right, now, so this is the map that we get. Now the map in Discovery is much prettier, but it's the same idea. All right, now, how do we interpret these clusters? So in other words, this is a set of records, this is a set of records, this is a set of records, and this set of records are all kind of similar to each other. This set of records are all similar to each other. This set of records are all similar to each other. So, but records, remember, are the customers. So this is a group of similar customers, a group of similar customers, a group of similar customers. So now we want to understand, well, who are these customers? What are they like? What are these customers like? What are these customers like? So Clementine gives you some ways to understand that. How do we interpret these clusters? How can we develop what we call cluster profiles? Consider the figure below, which is a bar chart of the clusters with a voicemail plan overlay. So we had 6 clusters, right? And we remember the nodes were like 0, 0. Remember going back to these nodes, 0, 0, 1, 0, 2, 0. So the nodes that were there were 0, 0, 2, 0, 2, 1, 0, 1, 2, 2, 0, and 2, 2. And the other ones, the other three, this is 6, so there were 9 altogether, so the other 3 didn't get any records, so we ignore those. So the 0, 0 node, this I guess is how many were in that node, how many were in the next node. So which was the biggest node, for example? This one, this one, 830. So this was the biggest one. And this is the percent. This had 24.9% of all the customers in that node. Okay, now now what? So now we have this. You can't really see. Well, yes, you can. We overlay color on this, and that is, remember, voicemail plan was a yes/no variable. That is, do they have voicemail or not? So we can see like this node here. Let's see, did I read this right? This is yes, and this node, okay, yeah, and this node or cluster was also yes, and these other ones were no. So clusters 0, 2 and 1, 2 contain records only if they are adopters of voicemail. That's kind of amazing. So these two clusters, everyone apparently had voicemail. So that tells us something about these two groups. These are voicemail groups, 0, 2 and 1, 2. While cluster 0, 0, 1, 0, and 2, 0 contains records if and only they have not adopted the voicemail plan. I'm so surprised that this is true. Oh, wait. Oh, there's a little difference. Yeah. Huh. It's kind of amazing. Cluster 2, 2 contains only a tiny portion of voicemail adopters. So there's just a little bit here of yes, right? So this is a very dramatic result, actually. This entire cluster, apparently, everybody in it is voicemail. And this entire cluster, nobody in it has voicemail, and so on. So that tells us something about the clusters. Cluster 2, this 1, 0, 2 and 1, 2 are they all have voicemail. Okay, so that's very interesting. Accepting this small proportion of records in cluster 2, 2, the clustering algorithm has found a high quality discrimination along this dimension. So it really is, what should I say, dramatic. It's not like, some of the, like 50% had voicemail and 50% didn't. No. It was like 0% here and 0% here and 0% here and only a very small percent here. So according to along this voicemail dimension, remember voicemail was a variable. We can talk about variables as being dimensions. So along this voicemail dimension, this voicemail dimension is what do they say? It's, what's the right word? It's very clear, very clear distinction. Okay, dividing the set nearly perfectly among adopters of voicemail and non-adopters of the voicemail plan. So that's remarkable if this is true. The figure also indicates to us the relative sizes of the various clusters. Yeah, we saw that. Clusters smaller than a certain threshold size may not be considered significant. Not sure about that, but that's what he says. With the threshold varying according to the size of the data set and the area of application and the task at hand. So maybe this cluster is so small that we don't consider it important, but I don't think that's true. I don't think that's necessarily true. Small might actually be good because it might be kind of uniform. So we might be able to understand it well because it's small and everybody, so with regard to all the variables, maybe everybody is the same. So that gives us a very clear understanding at least of this small group. Here, cluster 1-2 contains only 77 records, representing a rather small 2.31% of the data set. However, as we mentioned, it is nicely discriminating with respect to voicemail. In other words, everybody in there is voicemail. The distribution graph loses the geographic mapping information present in the original cluster plot. What do they mean by that? Well, this is the distribution graph, and this is the original one. Recall that because of the neighborliness parameter, clusters that are closer together should be more similar than clusters that are farther apart. So I don't know what closer together means, except that these are obviously far apart. I guess these are, this one and this one are further apart than this one and this one, I guess. I don't know if that's true, but consider the original plot. Here's the original plot. This time with an overlay of membership in the voicemail plan, shown below. Remember, we saw that some of the clusters were completely voicemail and some weren't. And here we're showing that again. They're showing the 6 clusters. We're showing them on the map. And this cluster was, I guess, all yes. And this cluster was all yes. And this one and this one and this one were all no. And this one was almost all no, but a little bit of yes in there. Okay? So what they're saying is these two are close to each other, as compared to, say, this one, and this one are not so close to these two. And they're also obviously close to each other with respect to whether they have a lot of voicemail people, right? So, so the fact that they're close together means that they're similar. And one way that they're similar, we see here, we see that they're, with respect to voicemail, they're similar. So this plot clearly illustrates the contiguity? I forget what that's not how you say that word, but anyway, how close they are of the two clusters, containing only customers who belong to the voicemail plan, and which therefore makes these clusters more similar. Cluster 22, how do we read this again? 2. So this one in the upper right also contains a few of these customers, but none of the clusters along the bottom row contain any customers who adopted the voicemail plan. So it's pretty amazing. At least with respect to voicemail, it's quite amazing. The clustering seemed to sort of is very much a function of the voicemail plan, right? And it shows, seems to be somehow related to the voicemail plan variable. But we didn't just include the voicemail plan variable. Next, consider the figure below. But now we're going to overlay down here international plan. If this is true, it's really amazing. I'm amazed that we can do this. I'd like to actually, if this is true, maybe Clementine is better than I thought in terms of showing this. This is hard to show anything like this in Weka, and even in Discovery. I haven't seen it shown like this, although you might be able to do something like this in Discovery. Clementine is really not so focused on visualization, first of all, and doesn't have, anyway, it doesn't even have Kohonen network. It has k-means as a clustering algorithm, but it doesn't have Kohonen network. Okay, let's keep going. Next, consider the figure below, which is again a distribution of the clusters, but this time with international plan as the overlay. So we have the same clusters here, same proportions and counts here, but we have the overlay is international plan. Now we can see that this one and this one are, it's amazing that this is so clear. It's not like half and half here. It's like 100% is yes in this one, and 100% is yes in this one. This time the clustering algorithm has found another perfect discrimination along this dimension. Remember, dimension means variable, and this is international plan is a variable, so we're talking about along that variable. Dividing the data set perfectly among adopters and non-adopters of the international plan. We see that cluster 1, 2 represents a special subset of customers. By the way, what was cluster 1, 2 before with respect to voicemail? It was yes for voicemail, and it's also 100% yes for international plan. So what now we might say, cluster 2, 1, 2, sorry, cluster 1, 2, everybody has voicemail and everybody has international plan. What does it sound like? It sounds like they're kind of big spenders, right? So this might be a group of kind of big spenders. But anyway, let's continue. We see that cluster 1, 2 represents a special subset of customers, those who adopted both the international plan and the voicemail plan. This is a well-defined subset of the customer base, which perhaps explains why the Kohonen network uncovered it, even though this subset represents only 2.31% of the customers. In general, not all clusters are guaranteed to offer obvious interpretability. So that cluster 1, 2, that was pretty obvious. They're kind of big spenders. So now we know we have like a group of sort of like big spenders. Okay, the data analyst should team up with a domain expert. Remember, domain expert is like, so this data analyst is someone who just runs us through Clementine or runs us through Weka, but doesn't really know anything about the business. But a domain expert is somebody who knows about this particular domain of where the data came from, or in this case business, or in this case telephone business. So the data analyst should team up with a domain expert to discuss the relevance and applicability of the clusters uncovered using Kohonen or other methods. So we could use Kohonen clustering, or I guess he's saying some other kind of clustering. Here, however, most of the clusters appear fairly clear-cut and self-explanatory. To complete the profile of our clusters, so we want to understand our clusters, we consider the cluster mean values for the numerical variables. Now, remember, in the last two cases, we were looking really not at numerical variables, but yes-no variables. International plan was a yes-no variable, and so was voicemail. But with so it's kind of, well, anyway. So we can also look at do some things with our numerical variables. So let's look at our numerical variables. So what were the numerical variables that we considered? Account length was a numerical variable. Voicemail message, well, I forget what that was. Oh, that was like the number of messages. Day minutes, that was the number of minutes used during the day, the number of minutes used during the evening. So these are all numerical variables. I guess customer service, for example, is how many minutes. No, it's probably how many customer service calls they made. But this is the average. So we're talking about in cluster 0, 0, that represents a group of customers, and they averaged 1.467 customer service calls. Their international minutes were averaged at 10.2 international minutes. Maybe this is per day or per week, I don't know. I forget. And there must be per week. That's too many hours, right? Too many. 209 night minutes, minutes per night. 200.249 minutes in the evening, and so on. So we have these averages for this cluster, and the 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 averages for all of them. Now, which was the one that we clearly identified? That was 1, 2. Let's see. Let's look at 1, 2. What else can we say about them besides the fact that they all did voicemail, and they all had international plans? So, what else can we say about them? The length of time that they'd been a customer was relatively long, but not as long as this group, right? The number of voicemail messages was more than, some of them I guess didn't have voicemail, but among the ones that did, even this group and this group, these guys were bigger, did more voicemail messages. How about here? Number of minutes during the day was relatively high. It wasn't the highest, but it was relatively high. Number of evening minutes, it was the highest. Number of night minutes, it wasn't the highest, but kind of in the middle. The number of international minutes was a little bit higher, but didn't seem to make too much difference. And the number of customer service was kind of low. Okay? So we can see that that kind of confirms that they're kind of big spenders. Okay, so let's read this again. In general, not all clusters are guaranteed to offer obvious interpretability. This one is still pretty clear what it's about. The data analyst should team up with a domain expert to discuss the relevance and applicability of the clusters uncovered using Kohonen or other methods. Here, however, most of the clusters appear fairly clear-cut and self-explanatory. To complete the profile of our clusters, we consider the cluster mean values for the numerical variables as shown. So now they go on to describe or try to give a profile for each of these 6 clusters. So cluster 0, 0, they call newbie heavy users. Does that look right? Cluster 0, 0, why do they call it newbie? Because the account length is short relative to the other ones. But they say heavy users. Why do they say heavy users? Because they use a lot of the most day minutes, not the most evening minutes, but a lot, and the most night minutes on average, and the reasonably large, I guess, relatively speaking, international minutes, and customer service, I don't know. I guess it's low. So they call them newbie heavy users, belonging to neither the voicemail plan nor the international plan. So that, this was 0, 0. So that you can see 0, 0 was not international plan, and it also was not voicemail plan. So they don't have voicemail, they don't have international, but they're still newbie heavy users. Belonging to neither the voicemail plan nor the international plan, customers in large cluster 0, 0 represent the company's newest customers, on average, with easily the shortest mean account length. These customers set the pace with the highest mean day minutes and night minutes usage. Okay, so we can characterize that we have groups, and one of these groups is like newbie heavy users. So you might not have known that there would be newbie heavy users. You might have known, of course, that there would be newbies, because of course they're new people. There's a group of people that you could characterize as being new customers, but you wouldn't necessarily know that there are newbie heavy users. But this SOM map or this Kohonen network found that out for us. Cluster 0, 2, what was that? 02. So they were not international plan, but they were voicemail plan. So cluster 02, this large cluster, it was a large cluster, it had a lot of records, 830 records. Contains members of the voicemail plan with therefore a high mean number of voicemail messages and no members of the international plan. Otherwise, the cluster tends towards the middle of the pack for the other variables. So they are, well, they're going to call them voicemail users. Just voicemail users. Okay, so that's how they name them. So the thing is about this kind of analysis is coming up with a good name for the cluster. Okay, that's the tricky part. Okay, now in 00 it was pretty easy to do. Newbie heavy users. Okay, now this one, 02, it's not so easy, I don't think. They come up with the name voicemail users because everything else was just sort of the same, but they all used voicemail, so that they called them voicemail users. But there were other users that are voicemail users, so it's a little hard to come up with the right name. His name is a little arbitrary, but this is kind of the art of cluster analysis. Cluster 10, average customers. That's interesting. Average customers. Cluster 10. So I guess they were sort of right in the middle with respect to all the variables, maybe, I guess. Customers in this medium-sized cluster, so it wasn't the most members, 10, but it had a fairly large number. In this medium-sized cluster, belonged to neither the voicemail plan nor the international plan, except for the second largest mean number of calls to customer service. So they did make a relatively large number of calls to customer service. This cluster otherwise tends towards the average values for the other variables. So they're just going to call them average customers. Again, not so easy to come up with a good name. So his name is pretty good though, I guess. Customer 1, 2, we already did that. I called them big spenders. He calls them power customers. This smallest cluster contains customers who belong to both the voicemail plan and the international plan. These sophisticated customers, so where's he come up with that word? Don't know. Again, it's kind of an art. Also lead the pack in usage minutes across two categories. So they use a lot of minutes in two categories and are in second place in two other categories. The company should keep a watchful eye on this cluster as they may represent a highly profitable group. Okay? Loyal, low usage customers. So we have another group of our customers which are loyal, but they don't use the service that much. So that's 20. Going back to 20, you can see they've been there for the longest period of time, 140 days, I guess that is. Doesn't seem like that long, but other than that, though, they're probably low with respect to these other variables here. Okay, so they call them loyal, low usage customers. Belonging to neither the voicemail plan nor the international plan, customers in large cluster 20 have nevertheless been with the company the longest, with by far the largest mean account length, which may be related to the largest number of calls to customer service. With by far the largest mean account length, which may be related to the largest number of calls. So they also make a lot of net calls to customer service. That's kind of strange. This cluster exhibits the lowest average minutes usage for day, evening, and international minutes, and the second lowest night minutes. And finally, cluster 2.2, the international plan users. This small cluster contains, well, if you want to go back and look at it, 2.2. So they have international plan, they don't have voicemail plan, and here we can say what? This is medium, this is small, voicemail messages. This is long, relatively long, relatively lot. This is low, and so on and so on. So what does he say about them? This small cluster, is it small? 240, I guess, a relatively small cluster. Contains members of the international plan and only a few members of the voicemail plan. So remember, that was the one that just had a few voicemail actually. The number of calls to customer service is lowest, which may mean that they need a minimum of hand-holding. Besides the lowest mean night minutes usage, the lowest mean night minutes usage, this cluster tends towards average values for the other variables. So what? How can we use this information? Cluster profiles may of themselves be of actionable benefit to companies and researchers. They may, for example, suggest marketing segmentation strategies in an era of shrinking budgets. So if you know that your customer is like a loyal, low usage customer, you might suppose they go when they have to visit your website, for example. So you can tailor, this is what Amazon does all the time, right? They bring up advertisements based on, based on who they think you are, based on your profile, right? So if you have some understanding of your customers, you can bring up the right advertisements, because when they come to your website, you might hope that they're going to buy something, even if it's your phone website, you might be trying to sell them something, who knows, like a headphone or something like that. Anyway, you might want to bring up the right kind of advertisement, because if you bring up the wrong kind, they're not going to buy it, so you'll lose a chance to sell them something. But if you bring up the right kind, then they only come to your website once in a while. But if you give them the right advertisement, then you might make that sale. So you want targeted advertisements, right? So they may, for example, suggest marketing segmentation strategies in an era of shrinking budgets. Even if it's not shrinking budgets, you want to target. Rather than targeting the entire customer base for a mass mailing, this is kind of an old idea, because people don't do mass mailings anymore, right? Everything's done by email. But even still, if you start getting email from a company, you might get pissed off, and you might block their email, right? But if they could send you email that you actually, of something you actually wanted, you might not block them, right? So so you might want to customize your email. They're talking about something a little different here, targeting, but it's sort of customizing it. Rather than targeting the entire customer base for a mass mailing, for example, perhaps only the most profitable customers may be targeted. Yeah, that's one way to do it. But that's not really relevant when we're talking about the internet. Another strategy is to identify those customers whose potential loss would be of greater harm to the company, such as customers in cluster 1, 2 before. And so you might identify those customers and, I don't know, give them some special treatment or something so that you can keep them as customers. Finally, customer clusters could be identified that exhibit behavior predictive of churning. So you might be able to find some clusters that you think represent possible churning candidates, and then you might do something about that. Intervention with these customers could save them for the company. Oops. Okay, so that's the end of our discussion of some maps, or self-organizing maps. Kohonen networks are also called. And now, if you take a look at the video about discovery, you'll have a little richer understanding of what discovery does, because it's a Kohonen map, and it has colors and so forth. But it does, actually, it probably does have these kinds of overlay graphs that we saw, but we're not going to be using them right now.